Welcome everyone to the seminar. We have already full room in the Zoom as well. So today we have the pleasure of having Gustavo Valdivieso to talk about the X ARAPUCA technology for the detection of scintillation light from liquid argon. Gustavo graduated in physics at the University Estadual de Campinas in 2008, and currently he is associate professor at in Brazil at University Federal de Alfenas. Gustavo has a background in scientific computation and data analysis, and also he developed his career mainly around neutrino physics. Then later on, he felt the need to complement his activities also with experimental physics and instrumentation, where he got where he was supported by Fermilab. And he contributed to the double choose experiment, the short baseline neutrino detector, and is now also part of the DUNE collaboration. So thank you, Gustavo, for coming, and please you can start.
Thank you.
Okay.
Okay, so first of all, good morning, and I want to thank you everyone for coming, seeing this presentation, and in particularly, I want to thank you, José Manera, Fernando Barão, that are here, that invited me here to come to Chile, to meet you, every one of you, and work with them. So this has been a wonderful week, very productive, and I hope you like the presentation. There will be 10 minutes at the end, right, for questions, but don't feel shy to stop me at any moment and ask questions. We're going to talk about trapping light for particle detection. And this is an explanation of the X ARAPUCA technology. And let's start from the beginning. What does this word mean? What is an Arapuca? So in the Guarani language of the native inhabitants of Latin America, Arapuca means a bird buster, or yeah. I could, let me see, separate the word, and ara is bird and puka means exploding or busting a bird, right? But what it actually refers to, it's this rudimentary trap where the bird or a small animal or a bird comes in and it trips over this piece of wood and the trap falls over the bird. And we are going to do the same with light. So now, the Arapuca, with all capital letters, refers to this novel technology invented and developed by Ana Amélia Machado from Brazil and Anthony Segreto, who is an Italian physicist, but works in Brazil. And they created this concept, and you can read all about the history or the story about how they came up with this idea in this edition of the Symmetry magazine. And they got, I'm going over the principle later, but suffice to say that it's a clever idea, which got them several prizes and recognition for this invention. So the Arapuca is actually a family of devices, not a single device. And again, in a few moments, I'm going over the principles, the fundamentals of how they work, and we're going to see a few differences in their evolution. But all of these are Arapuca devices, and you will probably notice right away that they all have something in common. They look like a mosaic with the same shape, getting bigger every time as we need. And this shape is the shape of the decorate filter. I'm going to talk about it in a moment, but now just pay attention that this is a limiting factor in the form factor of the Arapuca. Because of the way this filter is manufactured, it can't be very big, So when we want bigger Arapucas, we just make a mosaic of these tiny windows, right? But how does it work? Why is it so clever? So the Arapuca device is meant to detect scintillation light coming from liquid argon. On the left, we have the liquid argon medium. On the right, a representation of how the Arapuca works. So liquid argon, when a particle passes through it, leaves a track of ionized argon atoms, and then the scintillation light emitted is 127-ish, between 127 and 128 nanometers. These lights can be detected directly using silicon pions, for instance, which is the detector that you use. So in any case, we should be completely blind to this kind of light with our current electronics. And then comes the Arapuca. So the Arapuca is a series of basically three optical elements, which the first one is a wavelength shifter that gets this light and shifts it to longer wavelengths so it can be detected some way or some shape or form. Right after this, there is a direct filter that allows the spectrum of this shifter to pass through it. But then on the inner side, there is a second shifter that reabsorbs this light and re-emits it. But now it's off the transparent window of this filter. So the light gets trapped. All these surfaces are highly reflective, and the light can get back out. Because now it has an even shorter wavelength, and it can't pass through the filter. And inside, you can use, in principle, any kind of photon detector. Here we use silicon photon multipliers. So the spectrum, the emission spectrum of this shifter has to be tuned to the sensitivity of this silicon pion. So this is the first generation of Arapuca. But you are going to hear me talk a lot today about the X Arapuca. So the X Arapuca is an enhanced Arapuca, and this is the one that we are going to use in Dune, the Dune experiments. So what changes? If we compare both pictures, the second shifter is now used as a doping element inside a light guide. So we have a plastic or an acrylic light guide, and it's doped with the second shifter. Now, light comes, it's converted by the first shifter, goes through the filter, and then part of this light, around 60%, gets converted inside of, almost 100% of the light is converted inside the bar, the light guide, but around 60% of this converted light gets trapped by total internal reflection. And then it's guided through the silicon pion. The inner surfaces remain reflective, so light that doesn't get trapped, the other 40%, still have a good chance of reaching the silicon pion. So this is the fundamentals. In reality, as I showed you before, it looks more or less like this. This is an example of a dual cell. So we count the number of cells. This is a dual cell with two windows. And inside it, we have a single bar of wavelength shifter. The guide is a single bar. And we have 4 silicon pions on each side, here, 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 4 on each side. And here you can see, this is one of the photon detection elements. It's a frame with PMTs and 2 different types of Arapucas being installed at the SBND detector at Fertilab. For Dune, we are going to use what we call a supercell. So a supercell has 6 of those windows arranged in a different orientation with a single light guide surrounded by 48 silicon PMs. Each supercell has a little bit more than 1 meter in length, and we join 2 of them with a single electronics, and we call this a module. This is just for mechanical reasons, for make it easier to install in an APA, students APA. But the thing is, this module is actually composed. I'm sorry, let me correct myself. Each supercell is 50 centimeters, it's half a meter, and here we have 4 of them forming a module in a total of a little bit more than 2 meters. And all of this produces a single signal. So all the silicon PMs are gamed together to produce a single signal detecting lights inside the dunes volume. Okay, I'm going to show ahead in a moment. I'm going to show the simulations that I work on. But before we get there, I like this diagram very much. It helps me, guides me when I'm dealing with the Arapuca. So let me show it to you and see if it can help us understand a little bit better the principles. It's an energy diagram, and it shows the main elements of the Arapuca in order. And instead of focusing on the wavelength, we can focus on energy. So the light coming from liquid argon has around 9.8 electron volts. The first shifter converts it down to around 3.9, 3.4 electron volts. Now, this is able to pass through the electrolytic filter, which is actually an optical band pass. So it has a band between 3.1 and 4 electron volts. So this light can pass through it. It meets the light guide. So the light guide converts it down again in energy between 2.7 and 3 electron volts. And now it fits in the sensibility window of the silicon PN. And again, light that doesn't get detected right away reflects either trapped in the guide or between the reflectors, and it can't get back out through the electrolytic filter. Okay, now I'm going to go a little bit more detail through the materials that compose the Arapuca, right? I mentioned before that the idea of the Arapuca, it's a clever device, but for it to work, it has to be fine-tuned. Its characteristics of each one of those layers, they have to combine, of course. So the first layer, the first wavelength shifter for liquid argon, we chose the p-terphenyl, which we abbreviate as PTP, and it absorbs the 127 nanometers light from liquid argon and re-emits it with this spectrum, which above 50% emission lies between 320 to 370 nanometers. The layer itself is deposited over the electrolytic filter window with a thickness such as to allow for 100% absorbed light. So 100% of the 127, 128 nanometer light that comes through it is absorbed. However, the re-emission, this spectrum, is re-emitted isotropically, which means half of the light gets lost. Anyway, so light goes, the shifter fluoresces and re-emits light in all directions, half of it in the direction inside the box, the other half goes out. So remember that number, we're going to use it later. Then light goes through the filter, and we may have different types of filters depending on this first shifter. This one was designed to let light at 45 degrees incidence go through it. And here you can fit the spectrum, the PTP spectrum, inside this purple curve. which is 45 degrees. Why 45 degrees? Because the way these filters work, they have different transmittances and reflectance depending on the angle of incidence. So we had to tune it to some angle. And as the distribution is isotropic, we chose an average angle of 45 degrees. But it still transmits in other angles, as we can see. It's just it isn't as efficient as 45 degrees. Now, light goes through the filter and reaches the light guide. So the light guide is a commercial Elgin light guide doped with this proprietary shifter, which they call EJ286. And this actually makes it a little bit, I won't say harder, but interesting to work with the kind of work that I do, which is simulating the X ARAPUCA in a way that helps people developing the device itself. Because I have to know how this guy works. I have to know the spectrum in a level of detail beyond what is given to us in the data sheet. So here, this is what the company gives you through the specification of the material. But for my simulation, I had access to other kind of information that I can show you. So here you can see the PTP spectrum. So remember, half of the light that reaches it goes through the ARAPUCA and has this shape, this spectrum, and the absorbance spectrum of the light guide is the red one. So basically, all of this light gets, and then we emitted with even longer wavelengths in this region. And it shines blue under UV light. I mentioned that around 60% of the light gets trapped inside the light guide. And that's because of the combination of refraction indices between the liquid argon, which is filling the ARAPUCA, and the index of refraction of the light guide. So when light goes in, if it comes from outside, so this is interesting. When light comes from outside the light guide, like this, right? It will always reach the reflective material at the bottom and go back through. There is no way, if the light didn't originate inside the guide, it will never get trapped by total internal reflection, right? If it comes in, it must go out. But the concentration of shifter here was calculated to make it absorb around or close to 100% of the incoming light. So now light is converted, it's re-emitted in all directions. Again, it's isotropic, but light that is reflected outside this pinkish cone gets trapped. And because of the geometry of this bar and the relation between the reflective indices, this is around 57%. That doesn't mean that the rest of it, that the other 43% gets lost, because the rest of it will get out of the guide, but it's trapped between the night quark filter and the reflective material at the bottom. It's just that it's subjected to a different reflection pattern. So this is the enhancement of the X ARAPUCA. It's the effect that this light guide makes, guiding light through to the silicon PMs, which should be around. Speaking of which, this is the sensibility spectrum, or the efficiency, the photon detection efficiency of the silicon PMs that we are using. This is the worst case scenario. When we polarize the silicon PM, it has a peak efficiency around 40%, but we can use an overvoltage of a few volts to make it so that the average efficiency inside the spectrum of the light guide reaches 50%, which is the desired behavior for us. Also, the specific silicon PMs that we use are designed to work in cryogenic environments. Okay, so this is how it works. But why is it that Doom, and I'm going to show it in a few seconds, but why is it that Doom selected this technology in place of others? So let me talk a few numbers with you. This is the maximum theoretical efficiency of the Arapuca. Remember those numbers, we saw them through the slides. So it's 50% of the first layer, 80% of the, this is from the here, 80% is the average transmittance at 45 degrees. 57% of the light gets trapped inside the guide, and 50% of it with overvoltage gets detected at silicon PM, which has a maximum theoretical value of 12%. It doesn't seem large. The silicon PM itself detects 50%, but it's actually pretty good. And it doesn't get to that value at all, actually, because the real efficiency measured lies between 2 and 3%, which is still pretty good. How come it's, I keep repeating, that's good. It's only 2 to 3%, but if you think about it, the silicon PM has an area of 6 millimeters square, and we have 48 of them, which give us, if I only count the silicon PMs, we have 288 millimeters square of detection area. But the collection area of the supercell for Doom, so it's 6 of those filters, each one has 7,800 millimeters squared, which gives us this big number, which is 162 times the collection area of silicon PMs. And this is an expensive element for you to have in your system, right? The cost is very prohibitive. If I just said, okay, money doesn't matter, right? Let's cover everything with silicon PMs. No, we absolutely cannot do that. But it gets better because we may be tempted, we shouldn't, but we may be tempted to actually multiply each of those by their respective efficiencies, which is 50% for silicon PMs, and only the 2% in the worst case scenario for the Arapucas. And then we get a relation between effective areas, which is 6.5 times between them. But we shouldn't do that because remember, the silicon PM is blind to the liquid argon light. So when we do this, it would seem like we're saying that silicon PM can detect 50% of their liquid argon light, but it can't. So I'm coming from a blind sensor, 50% efficient to a certain band, but blind to the light that I have in my detector, and arriving at a 2% effective sensor, which is 162 times larger collection. That's the combination of numbers that makes this technology attractive. And where are we going to use it? I showed you the photo detection system elements for the SBNG detector, but I won't talk about SBNG today. Let's focus on Doom, because on SBND, there will be just a few Arapucas combined with some photo multipliers. But on Doom, they will be 100% of Doom's photon detection system. This is the only optical element inside Doom's photon detection system. So for those who don't know, let's talk Doom for a slide. What is the deep underground neutrino experiment? So the neutrino detector that will produce, so it will detect a neutrino beam coming from Fermilab that goes through the Earth's crust for 1,300 kilometers, reaching the fire detector in a mine more than 1 kilometer deep. we have two detectors. Actually, we have two detector sites, a near detector site and a far detector site with several detectors. I didn't use a picture for the near detector because there are no Arapucas in the near detectors, but it's foreseen that we're going to build 3 near detectors with different capabilities. And this near detector complex is going to house the 3 detectors so that we can characterize the neutrino beam before getting too far ahead of the neutrino source. And the idea here is to compare this knowledge of the beam before traveling to what we can see more than 1,000 kilometers away to measure neutrino oscillations and determine the final few parameters missing from the neutrino mixing model. Sorry. And the far detector site, as I said, it's more than 1 kilometer down the mine shaft. And here you can see the elevator, neutrino beam coming from this direction, and the site supports 4 modules, each one with 10 kilotons of liquid argon. And we have the fire detector 1 and 2, which will have different technologies. Fire detector 1 is the one that is far ahead in development, and we are in the beginning, not so the beginning anymore, right? It's pretty much established, but this one is a few, let's say 1 or 2 years behind the other one, and it will use Arapucas, but it will use again a new revision of the Arapuca. The geometry of the detector is different, so each one will be different. So for the first module, this is what we plan. Right? This is a human being for comparison, for a size comparison. It's a series of layers. Each one of those layers, it's a time projection chamber filled with liquid argon with alternating anodes and cathodes. So here you have the source for the electric field, it's a cathode, and surrounded by 2 anodes, then a cathode, and surrounded by 2 anodes. And the electric fields, they point in the direction of the cathode on each side, right? And away from the anode. To attract the electrons, make the electrons drift towards the anodes. And the anodes are where the photon detection modules reside. So each one of these have, so it's 1, 2, yes, so each one of these frames, it's an APA frame. It has 10 of those modules, each module with 4 supercells. And here is a real picture of one with 2 meters, right? So just a few numbers. There will be 1,500 modules or 6,000 supercells, 36,000 filters, or 280,000 silicons, right? Okay. Any questions until now? So if you allow me, I want to talk a little bit about my work, about what I actually do. So I work with simulations, and the idea of the work that I do is the R&D group is located almost 200 kilometers in another university, and we work together in Brazil. And they are the ones that are actually designing and improving the X ARAPUCAs, but everything they want to test can be tested first in the virtual Arapuca that we design. So the simulation is the completely non-imaginative name. It's the Arapuca sim. And it was designed with the GM4 library. But it uses it as a backbone, but it's actually has a completely independent system, which works like a virtual lab. So my philosophy behind this simulation is that, for instance, if the R&D group gets a new filter and they want to test, they will measure the transmittance of that filter. So they will go to an equipment and they will measure. I can get this relation and simulate the same equipment to compare their measurements to the simulation. And that way I can fine-tune each element, each material that goes inside the Arapuca separately, so that when we combine them, I get a better representation of the Arapuca device. So here are a few studies. The projection, sorry about the colors. Now that I see that the projection is not dark enough, but this is a simulation study of how light disperses inside the wavelength shifter. Because a photon coming from the dichroic filter, when it's converted in a certain point, and here I'm injecting photons into the light guide, always in the same point, right? But what changes between those two simulations is just how polished the surface is. So this is something that comes from the manufacturer. It tells us, okay, the level of polish of this light guide is such and such. And then I have to understand, okay, what does that mean? How does that translate to how lights travel inside the light guide? Because it's not ideal, right? If I said, okay, this is an ideal prism using transparent material, then we would just see light perfectly reflecting everywhere, but that doesn't happen in real life. So here I modeled the way light reflects inside the light guides, and changing the level of polish, I see that we go from a conical dispersion for high specular reflection to an elliptical dispersion for low specular reflection. And then we compare a continuum measurement here. We compare a continuum measurement of this parameter, how well polished the guide is, to the observed efficiency of the light guide. So I can determine, okay, when the manufacturer tells me in some engineering form how well polished that light guide is, from our measurements, we know the parameter that I have to input in the simulation to replicate that effect. And here we can see the dual cell with a light guide, single light guide behind those two windows. And in these two situations, the one more reflective or more polished or less polished, we can see the efficiency map on top of the acceptance window of the. So I generated photons coming from the liquid argon going into this window and being detected by these red traces here, which are the silicon pianos. And as you can see, the more well polished, the more specular is the reflections inside the light guide, the better the efficiency. So as I mentioned before, depending on the manufacturer, depending on the size and shape of the light guide, the average, the efficiency of the Arapuca ranges from 2 to 3%. And we can see that here. We did other studies. So one of those was a proposal to enhance the untrapping of those photons, because the silicon PM lives outside the light guide. And there is a way to use an optical glue and glue the silicon PM to the light guide, which makes the untrapping more trivial, but that's not the way that we are going to build it. We're going to build those ARAPUCAs right now, because there is another effect, which is the contraction due to the thermal expansion effect, which is another study that I also. So how to solve for the small gap of liquid argon between the silicon PM and the light guide? And that makes it so that light coming to the silicon PM will only go through if it comes in a cone with less than 51 degrees. Otherwise, it is trapped. So here you can see the incoming light. This is the angle of incidence, and light inside of this purple histogram can go through because it's it's inside the 51 degree cone, and it represents around 35% of the light. So this is one of percentages that we didn't use in that estimative. I mentioned that it's something below 12%, but because of this effect, if you get 1/3 of 12%, you go to a value more close to 3 to 4%. So what can we do about that? If we just leave it here, this is the incoming light, and this is the light that gets outside the light guide in the direction of the silicon. You can see that the purple light goes through. It's not 1-to-1 because there are other effects in play here. But the yellow light is trapped due to total internal reflection. So we proposed to make some sort of cut. Here it has a triangular form, but we also did for a circular form. And keep in mind that the silicon PM is very small. So in reality, this would look more closer to a corrugated surface, right? It's just a little detail on the surface. And just by doing this kind of cut with a certain angle, we can increase to twice the number of photons that gets extracted from the. And here, I changed the depth of that cut in millimeters and observed the increase in photons reaching the silicon PM. So this is how much extra photons got there. And for two different silicon PMs, one closer to the center and one on the edge of the X ARAPUCA. And we can see that for a certain value, we get to 100% increase, which is what I mentioned before, double the number of photons. This, there is no ARAPUCA built with this yet, but laboratory tests show that this effect is real. It can actually be done. It's more a problem of an engineering problem of building the light guide with this kind of searches on the sides. And I mentioned the thermal expansion. So the silicon PMs, they are fixed on the sides, on every side of the light guide, on the purpose, along the longitudinal sides of the light guide. And this is done in room temperature. But when we cool this to liquid argon temperatures, a gap forms around 0.5 millimeters. So now the question is, if I do nothing about this, if I don't use a optical glue, if I don't use some sort of spring to keep the silicon PMs touching the light guide when it cools, what does it happen to the number of photons? And for this, for the expected contraction, we can see a decrease up to 10%. So this is an effect that, again, it plays against the workings of the X ARAPUCA, and there are proposals of how to deal with this, but it's something that we have to keep in mind. We're coming to an end, and this is just our the list of references that I use. Those are papers, publications related either directly to the X ARAPUCAs or indirectly, like our Proto-Dune paper, which has a whole section describing the way the ARAPUCAs behave inside Proto-Dune and justifying why we were the ones picked up for Dune. Thank you.